Okay, so we have a special relationship that happens between number systems. So basically we have different types of numbers in mathematics. We have what are known as real numbers, rational numbers, integers, whole numbers, and irrational numbers. And basically this is just how those things relate to each other. So the way that we think about real numbers is real numbers are just all numbers that basically exist. They can be positive, negative, large or small, whole or decimal numbers. So basically when you think of real numbers, think of all the numbers. Those numbers are then divided into what is known as rational numbers and what are known as irrational numbers. Rational numbers are just ratios that can be made by dividing two integer numbers. So basically we can make ratios out of these numbers. And then irrational numbers are numbers that cannot be written as a simple fraction. We often see something that looks like pi in that, anything with a square root, and something that can't necessarily be, it can be a square root, but you can't find the square root of that number so easily. That would be your irrational numbers. Whenever you get into rational numbers, then you get into integers, whole numbers. So basically what whole numbers exist first, and whole numbers are basically positive numbers. Then you get integers. Integers include everything that's in the integers section and everything that's included in the whole number section. So an integer is basically a whole number or a number that is not a fraction. It can be positive or negative. And then rational numbers would include rational numbers, integer numbers, and whole numbers. So it includes everything. And then rational numbers are just things that can be written as a ratio, things that can be written in fraction form, or simplified further into decimals. That's basically the gist of these different things. But what we're going to get into today is something known as complex numbers and something known as imaginary numbers. And so here are the definitions for those things. A complex number is basically a number in the form a plus bi, where a and b are real numbers and I equals the square root of -1. What we'll also identify is that I represents our imaginary number. Imaginary numbers are numbers in the form of bi, where b is the real number and I is equal to the square root of -1. We'll also learn that I just represents our imaginary number. So what even is an imaginary number and how do we get to it? Well, let's think about the square root of -1. So say that I have an equation that starts like this. X squared is equal to -1. Okay? Well, there's a specific way that we go about solving this problem. And the way that we do that is we get rid of the square and the x, and we want to isolate the x to solve for what x is. So basically what we're going to do is we're going to apply the square root to both sides so that we can cancel out this square. That leaves us with x is equal to the square root of -1. Okay? This can also be written as x is equal to plus or minus the square root of -1. Because whenever we think of square roots, we can have positive values that give us square roots or negative values that give us a square root. For example, say I was looking for the square root of 9. The answer could actually be +3 or -3. And the reason is you can multiply +3 times +3 and get 9, or you can multiply -3 and -3 and also get 9. And so we often represent square roots as this would be positive, negative square root of 9. So basically we're just doing that same thing. Okay. 1 second. Just reference it. Okay. So here's where we end up. So this is saying is x is equal to positive or negative square root of 9. Okay. Well, the interesting thing about this problem is that there actually isn't anything that can give us the square root of -9. So what even is the square root of -9? Well, I mean, -1. Well, there isn't any. And so what we can actually do is we can create an imaginary number to act as the x value for the square root of -1. So the way that we would do that is x is equal to positive, negative, an imaginary number. And that's how we get to our imaginary numbers. So we can replace the square root of -1 with the imaginary number I. So basically what that gets us to is an imaginary number is a number that is of form bi, where b is a real number and I is the square root of -1. So basically I is equal to the square root of -1, right? Because we can use our imaginary number to act as our x, which is the result of the square root of -1. So because we don't have a square root of -1, we can make up an imaginary number, which is I. That's basically how we find what an imaginary number is. Okay. So basically, we just substituted the root of -1 with I. That's all we have to do. Okay, any questions? Questions, concerns? No? Okay. Okay, so now we're going to get into the syclic nature of the powers of I. So basically what we're able to do with this nature, and we'll look at what the pattern is, but basically what I'm able to do is I'm able to solve for what does I equal to, what does I squared equal to, what does I cubed equal to, and so on and so forth. And what we're going to notice is that our resulting values have this special power that can allow us to find basically the power of any I. So basically, if eventually I want to find the power of I-15 or I-34, what I'll notice is there's a special relationship that will allow me to do this. Okay, so what is I, the imaginary number I equal to? Well, we just discussed that I is equal to -1. Okay, I is equal to -1, and the square root of -1 is equal to I. So our resulting value is I. So the imaginary number is equal to the square root of -1. Square root of -1 is equal to I. We've already discussed that. What about this? The imaginary number squared. Well, the imaginary number squared is basically telling me to take an imaginary number and multiply it by another imaginary number. Well, we know that those imaginary numbers can be substituted by the square root of -1. Okay? That allows us to cancel these out, and that gives us -1. So basically, the imaginary number squared is equal to -1. Let me go ahead and color code this so we can see it better. Okay, what about I cubed? Well, I cubed is basically I squared times I. Why is that? You may be asking, because basically what you're doing is you're taking 2 and I to the power of 1. When you have 2 exponents that are multiplied together, you're basically adding them together, so they would give you 3. 2 plus 1 is 3, and so that's why we could use that. I squared is equal to -1. That's what we just solved. So I'll just plug that in. And I is equal to I. -1 times our imaginary number is basically just negative imaginary number. So what you'll see is there's a relationship. We're able to, here we plugged 2 in, here we plugged I in. What about 4? Well, basically 4, we could use I cubed plus I cubed. Again, why is that? Well, because if you add these 2 exponents together, 2 plus 2 is 4, so that's why we can use that. And you'll begin to see the relationship. -2 is equal to -1, right? That's what it tells me right here. So I just do -1 times -1. -1 times -1 is a positive 1. Okay? And so what you're actually going to begin to see is that these values are now going to be repeated. So I to the power of 5. What could I use? I could use I4 plus not plus I, times I. I4, we just solved for it. It was 1. I by itself, we solved for it. It's I. 1 times I is just 1. Now 6. Let's try 4 and 2. 4, we just solved for it. It's 1. 2, we solved for it earlier. It is -1. 1 times -1 is -1. Now 7, we can do 4. We could also do 3, right? Because 4 plus 3 is 7. So that's how we can do that. 4 is, we'll look down, -1. 3 is -I. 1 times -I is -I. 8. 4 plus 4 is 8. I4 is 1. Another I4 is 1. 1. So I'll show you more about what we're doing here in case you're a bit confused. Basically, it's pretty straight. Ooh, that's not what I meant to do. Okay. So from this pattern, what you can be able to see is that we start with these here. We start with I squared, I to the power 3, and I to the power 4. Okay? Given that, we get resulting, and I just want to make this a little easier to see. We get resulting values. So I to the power of 1 is equal to I to the power of 2 is equal to -1. I to the power of 3 is equal to I to the power of 4 is equal to 1. And basically what we're doing once we get to these larger values is we're substituting these in and using our resulting values to solve. So for example, here I put in a -4. I see that -4 is equal to 1, so I just plug 1 in. Here I include an I. I know that I is equal to just I, so I just put that in. And then I multiply those two together to get my resulting value. Same thing here. I put I to the 4. I to the 4 is equal to 1, so I'm just plugging that in. Here are 2. I'm putting a 4, so I just put that in. Here I put in 4, so I just put that in. Here's also 4, so I just put that in. So basically, I'm putting these resulting values in for that substituted variable right there. So I to the power of 2 was -1, so that's why I plugged in -1 here. I to the power of 3 was -I, so that's why I put in -I here. And then once I get to this part where I have my substituted values, that's where I can actually multiply across to get my resulting variable. And what you'll notice is that these repeat. And so here I had just an I, here I have just an I. Here I have -1, here I have -1. Here I had -I, here I have -I. Here I have whole number 1, here I have whole number 1. And that will actually repeat. So if I move to I9, I10, I11, those will repeat. So I'll start again. I, -1, -I, 1. And so basically what happens is we have a repeating cycle of these values. We have a repeating cycle of I, -1, -I, and 1. And because of this, we can solve for the power of any I. So say I'm looking for I15, or I'm asked to find the value of I15. Well, basically what I want to do is find out which exponents can I use from just these. These are the easiest ones to work with. So which exponents can I use here to get it to add up to 15? And what you can actually do is you could do I4 times I4 times I4 times I3. And why is that? Well, because you would get 4 plus 4 is 8 plus 4, 12 plus 3, 15. So there I made my exponents equal to 15, and now I just need to do my substitution. So I4 was equal to 1, so I just plug that in. 1 times 1 times 1. What is my I3? I'll look at it. I3 is negative I. Oop. This is supposed to be 1. I3 is negative I. And then now I can take those values and I can multiply. 1 times 1 is 1. Well, actually, if I do all these together, that get 1 times 1 times 1 is all 1. So it goes 1. And then times negative I. 1 times negative I is just negative I. So equal to negative I. So the imaginary number to the power 15 is equal to negative I. And so using that relationship and using what I know here about these first 4 values, I'm able to solve for any power that I want to. So I'm able to solve for 15, even though 15 wasn't on this original chart. Okay? Any questions about what I'm doing here? And then I'll post this chart for you. So you don't necessarily have to create it by yourself. You already have it, and you can reference this to be able to solve for any power you want to. Okay? But basically, that's how we're able to solve for any power. Okay. So now we're going to get into complex numbers. They're pretty simple. We're not going to do too much with them. We're just going to be able to plot them, which is actually a lot easier than you may think. So what is a complex number? Complex numbers take the form a plus bi. For example, I can have something that looks like 3 plus 2i. Again, I here is still my imaginary number, or I can have negative 4 minus 6i. Basically, what I have is a real number, and then I have an imaginary number, a number which is imaginary. And so that is what a complex number basically is. It has a real number and it has an imaginary number. That's how we typically see them. We can also have complex numbers, which are irrational numbers. Remember, irrational numbers cannot be simplified into a fraction. Most often or not, there'll be square roots that you can't simplify. So for example, an irrational number might be the square root of 2 minus the square root of 7i. Right? So those are just 2 irrational numbers. You still have a real number proponent and a imaginary number. Another unique thing that you can have is 0. So you can have where a is 0. And this would basically just give you 2i, because 0 plus 2i is just 2i. Or you can have where your b is 0, so 5 plus 0i. 0i basically means no I, so that would just equal 5. And these are just all different types of complex numbers that you can have. But what you can do with these is you can plot them, and they're super easy. Okay, so this is basically what we're going to take away from this. So real numbers. Real numbers are basically just numbers that we work with, whole numbers or negative numbers. You can plot all real numbers on a number line that is horizontal. So say I wanted to plot here. Say I wanted to plot my real number 2 and my real number negative 2. I would just plot them like that. So all real numbers go on a horizontal line. Okay, so here I can plot 2 or negative 2. Imaginaries, on the other hand, have to be plotted on a vertical line. So here I have 1i, 2i, 3i, 4i. And the reason I'm writing I is because I am including my imaginary numbers, right? So it has to include that I. So say I wanted to plot, well, here I plotted 2 and negative 2. Okay, say here I want to plot 3i. So I'm plotting 3i, and I want to plot negative 4i. So basically, the only difference between real numbers and imaginary numbers here is all real numbers need to be plotted on a horizontal line, and all imaginary numbers need to be plotted on a vertical line. Well, once we get to complex numbers contain real numbers and imaginary numbers. So say I wanted to plot 2 plus 3i. Well, 2 would be my real number, so it has to be plotted on the horizontal line. And 3 would be my imaginary number, so it would be plotted on the vertical line. So basically, that would look like, let me just draw some lines here. Okay, so 2 is my real number, so it has to be plotted on my horizontal line. So 1, 2. So there's 2. Okay. And 3i has to be plotted on my vertical line. So 1, 2, 3. Here's my 3i. So where those things meet, approximately right here. This coordinate right here is basically 2 plus 3i. So basically, that's how you plot complex numbers. All your real numbers go on your horizontal line. All your imaginary numbers go on your vertical line. And so complex numbers, they'll be plotted like this, where your real number stays on your horizontal, your imaginary stays on your vertical. And basically what you're doing is finding that point where those intersect. Okay, and so basically what you could do here is this coordinate would also be, my 2 is my x value, so 2, and my 3i is my y value, so it could also look like that. So you're just looking for 2 and 3i. That's that coordinate where that complex number exists. Okay. So say I had -1 minus 2i. -1 is my real number. -2i is my imaginary number. -1 would be right here. -2i would be right here. Where do those two intersect? Right here. And so that would be -1 and 2i. Give me 1 second. Hello. Yes, 1. So basically like that, you're able to plot complex numbers. Okay. So we're going to get into 2 more quick things. A lot of this is a review, but basically how do you implement complex numbers once you get there? So absolute value of real numbers and imaginary numbers. The absolute value is basically the distance from 0. So in real numbers, the absolute value, say we're looking for the absolute value of 2, it's basically the distance from 0. So here we have 0. And let's say I want to plot 2, or the absolute value of 2. The absolute value of 2 is basically the distance from 0. So 2 is 2 units from the absolute value of 2. So our answer would be the absolute value of 2 is just 2. What's the absolute value of -3? I'll plot -3 right here. Basically, the absolute value is just the distance from 0. So 1, 2, 3. So 3. Okay. Well, the same thing goes for imaginary numbers. So say I'm looking for the absolute value of 2i. Well, again, because we have 2i, we're plotting it on the y, on the vertical axis. So this is 2i. And so what's the distance from 0? Well, again, it's just the distance from 0. So 1, 2. So the absolute value is 2. What is the absolute value of -3i? Well, let's plot it. -3i is right here. What is the distance from 0? Your absolute value is equal to the distance from 0. So 1, 2, 3. Right? So the absolute value of real numbers and imaginary numbers are basically the same thing. Well, what if I'm asked to find the absolute value from my 0, 0 to what's plotted here is 4 plus 3i. Well, what you could actually do to solve this is you can use the distance formula to be able to solve for the absolute value of 4 plus 3i. And basically what you would do is you would use this equation right here. So we just plug that in. A is 4. So 4 squared plus b. What's b? B is 3. So 3 squared. Solve for that. 4 squared is 16. 3 squared is 9. 16 plus 9 is 25. The square root of 25, oh my goodness. The square root of 25 is 5. And so the distance, or the absolute value of 4 plus 3i is 5. So you can use the distance formula to also solve for the absolute value of a complex number. If it isn't so easy to go ahead and just count the distance to 0. It's easier to count the distance to 0 when you're on a straight plane, like this on your x or your y, but it's a little more difficult to count diagonally. And so if you have to count diagonally, all you have to do is plug it into this distance formula for your complex numbers, and you'll be able to solve. Okay, and then A is always going to be your real number component, and B is always going to be your imaginary number component, but you don't have to include that I. All you're including is the B. So in this instance, the B is only 3. And so that's why all we're including is 3. You don't have to include that I part, just the whole number part, the 3. All right, any questions about this? And basically, this is just showing you how you go from the distance formula to your formula for complex numbers distance. But basically, this is the equation you're using to solve for that distance or the absolute value of that complex number. All right. Okay. So what did we learn today? We learned about I. We learned that I is equal to the square root of -1. We also learned that the powers of I are cyclic, which means they repeat. So we start with I2 is equal to -1. I3 is equal to -I. I4 is equal to 1. And I to the power of 5 is equal to I. And these just basically repeat as you increase power values, but we can basically use this subset to find higher power values. So I'm able to find I15 just using these variables because they just repeat. So the values repeat can help you find any power of I. Then we got into complex numbers. Complex numbers take the form A plus BI. They have their real number component, which is A, and then their imaginary number component, which is BI. This is the imaginary number component because it contains that I, which is our imaginary number. Okay? Then we're able to go ahead and plot these. We're able to plot complex numbers on a plane. Remember that all your real numbers go on the horizontal, all your imaginary numbers go here. And then the point where they intersect would be where you plot that thing. So here, your real number is 2. Here, your imaginary number is 3i. You can plot those here, but where they intersect is where the imaginary number or the complex number exists. So right there would be 2 plus 3i. Okay? And then to find the absolute value of a complex number, basically what you want to do is use your distance formula to solve. This is your distance formula right here. And so say if I wanted to find the distance of 2 plus 3i, so I want to find the distance of 2 plus 3i, the one that's plotted right here. Well, basically, I just plug that in. So the A plus BI, it's basically taking a complex number form. So I plug that in. I need A squared. A is 2, so A squared. Plus B squared, B is 3, so I just plug that in. 4 plus 9. 4 plus 9 is 13. I can't really simplify that any further, so I'll stay right there. So basically, that is my absolute value of that complex number. Absolute value of 2 plus 3i is -13. Pretty straightforward. Okay. Any questions?
No, ma'am.
Okay. If there's no other questions, you guys may log off. Just remember tomorrow, I will post the practice problems video on the stream. Just watch that practice problem video and then just submit your independent practice and then you're good to go. So we're not meeting tomorrow. Just make sure you do those 2 things. And make sure to submit your check-in so I can count you present, okay? Bye, guys.
Bye, Miss.